Hello, in this video, we would like to talk about Jitsi Meet, how to install it in Ubuntu, how does it works, and analyze the package that I got from Wireshark capturing. Before that, let me introduce my team first. We have Angelina Jolie, Dedrick, myself Jackie, Raphael, and last but not least Winona. Let's start with installing Jitsi on Ubuntu. I'll follow all the steps provided by DigitalOcean's website. We start by setting up the system hostname. Copy this code here and open the terminal in Ubuntu. Then paste it into the terminal. Then change your domain to the domain you want. In my case, I'll change it to dowas.id. Then enter your password and click enter. Next, you can check the system hostname simply by typing hostname in the terminal. I will be setting a local mapping of the server's hostname to the loopback ID IP address, which is 127.0.0.1. Do this by opening the /etc/host with a text editor. Then add the following line and change your domain to the domain you choose. Press Ctrl O and enter for saving and Ctrl X for exiting. Next, we will be configuring the firewall. Just copy all this line of codes here and paste it in the terminal. This code I use to allow some port like port 80, 443, 4443, and 1000 to open up. After that, type in sudo ufw enable to enable, and then check the status by typing sudo ufw status. The next step will be installing Jitsi Meet itself. Just copy and paste these 3 lines to download and then delete Jitsi GPG key. Now, you will add the Jitsi repository to your server by creating a new source file that contains the Jitsi repository. Open and create the new file. Add this line to the file for the Jitsi repository. Save and exit the editor. Finally, perform a system update to collect the package list from the Jitsi repository and then install the Jitsi Meet package. During the installation of Jitsi Meet, you'll be prompted to enter the domain name that you want to use for your Jitsi Meet instance. Press tab and then enter. Then you will be shown a new dialog box that asks if you want Jitsi to create and use a self-signed TLS certificate or use an existing one if you have one. Just press tab and enter. Your Jitsi Meet instance is now installed using self-signed TLS certificate. This will cause browser warnings, so you will get a signed TLS certificate in the next step. Jitsi Meet uses TLS certificates to encrypt the call traffic so that no one listens to your call as it travels over the internet. Jitsi Meet supplies a script to automatically download the TLS certificate for the domain. Run this certificate installation script provided by Jitsi Meet. The script prints the following information when you run it and asks if you want to supply an email address. Just type in one and press enter. Now your Jitsi Meet is already installed. Go to Mozilla and type in HTTPS and your domain, and then let it load. This is the final product, and this is how Jitsi Meet will look like. Why Jitsi, you might ask? While looking at another video conference app, let's take an example here, Zoom. There is one big issue. Zoom is not end-to-end encrypted, it is transport encrypted. Meaning that when the message gets encrypted while sending from a client to the server, the message gets decrypted in the server, then re-encrypted to be sent to another client. In other words, Zoom can view and look in our message, can record our meetings, and in their server. This is obviously not legal, but Zoom can do that. While in Jitsi Meet, an open source alternative, works similarly to Zoom with an exception of it uses WebRTC so that you don't need to download any application. And since it's open source, you don't need to use the Jitsi Meet public server where your data or information can get decrypted. You could make your own server and host Jitsi Meet from within. Let's dive into Wireshark analysis by capturing the packets while I'm Jitsi Meeting. First, I need to go to Mozilla and type in jitsi.was.id. Then I'll need to create a new meeting. Then stop capturing the Wireshark. and let's analyze this packet in the Wireshark. Let's discuss about QUIC by first talking about its predecessor, TCP. As we all know, TCP starts with a three-way handshake, a SYN, SYN-ACK, and an ACK. It's already one network round trip, and we haven't encrypted it yet. So we need the TLS certificate protocol, which client send a hello and the server send back a hello. This takes another round trip, and now finally the application can actually begin to use the connection. This is why HTTP protocol, where client send a GET and the server send a response. Finally, this will be a total of 3 round trip if everything works fine. This will be no problem if you sit close with the server, but what if the server is located in another continent? It will really cost a lot of time. Now, let's see how QUIC connects. Since QUIC runs over UDP, there's no need to set up three-way handshake. We just save ourselves one round trip there. Then the first QUIC packet sent to the server already has the TLS hello. The server will reply with the server-side TLS and usually comes with a certificate of FIN-TLS. All of this in one round trip, and technically we are good to go. The client can send an application request in forms of HTTP protocols. Then the server can begin to send the data. So only 2 round trip and we are done. So QUIC stands poised to be at least 1 network round trip faster than TCP. In the Wireshark capture, you could see that the source 192.168.0.110 or my IP is sending all this variety QUIC protocol with different information to the server, which is 142.251.12.93. We could see initial, which is an initial step to connect between client and the server. Then a protected payload, which is the data that is being sent back from the server to the client, but it is encrypted. And we could see a 0 RTT, which is an information to the server to connect, and a handshake to telling the server to connect to the client. If the client and server didn't use the QUIC protocol, it can use the DTLS or data transport layer security. Essentially, it's just client sending a hello, then the server sends back a hello, a certificate, and a certificate request, followed by client sending a certificate and key exchange, and then the encrypted handshake message. It's all essentially the first step of QUIC. Session Traversal Utilities for Net, or STUN, is a standardized set of methods, including a network protocol, for traversal of network address translator gateways in application of real-time voice, video, messaging, and other interactive communications. The STUN client sends a request to a STUN server to discover its public IP and ports, and the STUN server returns a response. There are 2 types of requests: binding requests, which are typically sent over UDP, and share secret requests, which are sent over TLS over TCP. Binding requests sent from the STUN client to the STUN server are used to determine the IP and ports binding allocated by NATs, and then the STUN client sends a binding request to the STUN server over UDP. The server examines the source IP address and port of the binding request and copies them into a binding request that is sent back to the client. Real-Time Transport Control Protocol, or RTCP, is a protocol that works with Real-Time Protocol, or RTP, to monitor data delivery on large multicast networks. The purpose of monitoring delivery is to determine whether RTP is providing the necessary quality of service and to compensate for delays if needed. RTCP is used in voice over IP and Internet Protocol television, streaming media, and video conferencing. RTCP carries statistical and control data, while RTP delivers the data. RTCP statistics typically include the number of bytes sent, lost packet, and round-trip delay between endpoints. RTCP also carries the canonical name or CNAME, which is a unique identifier for a participant during a session. RTCP can use 5 different packet types to carry statistical and control data. The packets are RR or receive report, SR, sender report, SDES, or source description items, by indicates end of participation, and app, application specific functions. The User Datagram Protocol, or UDP, is a communication protocol used across the internet for especially time-sensitive transmission such as video playback and video conferencing. Compared to other protocols, UDP accomplishes this process in a simple fashion. It sends packets or units of data transmissions directly to a target computer without establishing a connection first, indicating the order of said packets or checking whether they arrive as intended. UDP packets are referred to as datagrams. In the Wireshark, we could see that my laptop and my phone are sending data to each other and to a Jitsi public server. When my laptop IP ends with 110 and my phone IP ends with 107, UDP is just a constant state of sending packet whenever a person is sending any form of data. Alright, this is the end of the video. I hope this video can be useful for anyone who is watching this.